In this video, we're going to look at rare events, the sample, the decision, the conclusion, any kind of additional information, and the full hypothesis test examples. So we're now in the land of doing testing of hypothesis. We have spent time gathering data. We have spent time finding the statistics of the data. So the mean, median, and mode of the data that we had. Presented the data in graphs and charts. Now we're going to make decisions about the data that we have. So let's first talk about what a rare event is. So we're going to decide to reject the null hypothesis if the sample outcome that we have done contradicts our own assumptions. The logic is as follows. To make the decision, we're going to calculate something called the p-value, and the assuming is our sample outcome or something more extreme occurring, assuming the null hypothesis is true. If the p-value is very small, our sample outcome is very unlikely. So in other words, it's a rare event. Recall that our assumptions is based on the null hypothesis. So rejecting the assumption is the same as rejecting the null hypothesis. The smaller the p-value, the larger the absolute value. When we talk about the larger in terms of absolute values, not being negative or positive, but the absolute value of that. The z or t-score. So that's the smaller the p-value, the larger absolute value of it, of the z or t-score it is. And so an unusual t or z-score gives us a hint about the p-value. Well, what is the p-value? The p-value is a probability that if the null hypothesis were true, the results from another randomly selected sample will be as extreme or even more extreme as the results obtained from the sample that we are looking at. A p-value is a probability. It is not the same thing as a proportion, so it's not p hat, p hat prime, or even p bar. This is a probability, not a proportion. When you make a decision, you're going to fail to reject or reject the HO, H-O, that's the null hypothesis. If the p-value is less than our alpha, we're going to reject the HO. The result is the sample data are significant, and there is sufficient evidence to conclude that the HO, the status quo, is an incorrect belief, and the alternative hypothesis, this is what we are usually trying to prove, may be correct. If the p-value is greater than or equal to the alpha, we do not reject the null hypothesis, we do not reject the status quo, and the result of the sample data is not sufficient, and so there is not sufficient evidence to conclude excuse me, that the alternative hypothesis, the thing that we're hoping to prove, is correct. So when you do not reject the HO, that is the null hypothesis, it does not mean that you need to believe the HO. It just means that our data that we have fails to provide a sufficient evidence that will cast doubt on the truthfulness of the HO. And remember, the HO is the status quo, stuff that is expected to be believed, and we are proving whether or not it actually is or not, sort of. So here's a memory device that may be helpful. If the p is low, the null must go. So you're going to reject the null hypothesis. There is sufficient evidence to lay some doubt on the status quo. If the p-value is high, then the null must fly. So in other words, we accept the null hypothesis, we fail to reject it. And when we're doing our hypothesis test, you're going to select an alpha. This is A, it says alpha, to use before you're going to collect the data samples. So if no level of significance is given, it's standard to use an alpha of 0.05. Now, if I make the connection between this alpha and confidence intervals, that's like saying I'm 95% confident, right? So the alpha would be 1 minus that 0.95, so in other words, 0.5. Cool, that's nice. How do we find the actual p-value? What is this p-value? How do we find it? The p-value is the area under the curve. We're going to use our calculators in Excel. Hopefully you'll build something that looks like these, or you can use your TI-83 or 4. They will also give you that. You're going to need a z-score. So assuming you're given a z-score, then you're going to make a decision based on that z-score. If you know sigma and mu, which doesn't happen very often, or if you're in the land of proportions, this is what you're going to use. They're the same thing, the same calculators, because it's the norm.dist. If you don't know that, so you don't know sigma and mu, you just know sigma but not mu, then you're going to use a t-distribution. So we'll undo it with a t-distribution. Now what I want you to do is I want you to put these in your spreadsheet so that you're getting the same numbers. This 0.05 is not the z-score, it's the alpha. And I will talk about why I'm doing this and why I'm actually going to be using z-scores and also to make that comparison as well. So if I want the left tail test and I'm going to do the norm.dist, I'm going to grab the cell that has the z-score, this green cell, put in 0, 1, and true. Now, because I am in the standard normal distribution, I could have used norm.s.dist and just grab the z-score and true, and I wouldn't have to put the 0, 1 in. Because remember, we're in z-scores, that means we are now in the land of standard normal distributions. We have made that conversion. So if I want the left tail, so the parameter, which is the value coming from the population, is less than the value I'm interested in, it is a left tail test, and I'm grabbing that area. If I want the right tail test, it is 1 minus the norm.dist. And then if I want a two tail test, I'm going to grab 2 minus the one up above, so the one to the right. And then I'm going to do the absolute value of the z-score. And you're like, why the absolute value of the z-score? Because we want to make sure that we don't grab a negative because of the way that we have symmetry. And you're like, I'm still not quite getting it. Okay. So when you are doing a two-tailed test, you want to grab the upper z-scores. So say your z-score lands down here. Your z-score is, say, a negative 1.53. That's your z-score, right? So what you want with the z-score, and you want a two-tailed test, if you just do the norm.dist, you're going to get this area here. Cool. If you do the 1 minus, you're going to get this area here. Cool. But what if instead of the area above and the area below, what if you want the tails? You want to cut this into two. So when you do the two-tailed test, if your z-score happens to be negative, say it was a negative 1.53, and I just do the 1 minus the norm.dist, then I'm going to get all of this area again. And I multiply it by 2, so I'm going to get a number that's going to be larger than 1. So what I want to do is I want to move this z-score to the right of the mean. So to move this z-score to the right of the mean, I need it to be a positive 1.53. The way I do that is I take the absolute value of that z-score. So then I'm finding this area up here. And I'm going to then multiply it by 2, and that will give me this area down here as well. So what happens if you just did the norm.dist? Why can't I just do the norm.dist and call it a day and multiply it by 2? Well, if I just do the norm.dist and I get, as you can see for this example, the norm.dist to the left is 0.5199. That is larger, by the way, if I multiply it by 2, than 1. However, if I do 1 minus the norm.dist, then I'm going to get the absolute value of the z-score, 0, 1, true, multiply it by 2, and then I'll get the actual probability of that, which is what I want. So that's why we put on the absolute value. Now, if we take a look at the next spreadsheet, I should say, this is what happens when we have t-distributions. This is what happens when we have mu, but not sigma. Notice with this one, I put in my t-score, and I do need the sample space size. It'll calculate my degrees of freedom by doing an equals. Grab this cell -1. The t-distributions are slightly different in the fact that I don't have to do the 1 minus if I don't want to. So the t-dot distribution, I'm going to grab the cell that has my t-score, my degrees of freedom, and I hit true. And this is the left tail. This is the left tail test. Now it has its own call for the right tail test. So if you want to do the right tail, or you can do 1 minus the t-distribution of the t-score. So if you want to be consistent as we do for the normal distributions, you can do it that way. but it has its own call, so we might as well just use it. So we do the t.dist rt, I grab the z-score and just the degrees of freedom, and I'm done, and it assumes that I am wanting the right side of that t-score. Now, it also, by the way, has its own call for the two-tailed test. And as before, we're going to make sure that we grab the absolute value just in case this z-score was negative. So we 2.dist.2t, parenthesis, abs, parenthesis, grab the cell that has a t-score, comma, grab the cell that has a degrees of freedom, hit enter, and this is what you're going to get. Now, these numbers I just put in so that you can check your numbers against mine. These are the alphas. I am not going to, most of the time, I am not going to find, once I know the alphas, I am not going to do this to find my z-score, because these numbers, these 0.05, are actually from up above. These are probabilities, they're not z-scores. So if your z-score was 0.05, this tells you you're pretty darn close to the mean. That's a z-score. So if your z-score is close to 0, that means you are close to the mean. These are numbers that not necessarily, they're actually not going to be alpha. They're period, not going to be alpha. These are just numbers so that you make sure that your numbers are matching up with mine. Now, if I want to find these p-values, deciding whether an alpha is equal to 0.05, this is the probability. So remember, HO is the alternative, or the null hypothesis. HO is the null, this is the status quo. And we see we're using P, which is the parameter notation for the population. So we are testing whether or not the parameter of 0.03 is greater than or equal to 0.03. The HA is always the opposite. HO always has equality. HA has the opposite without equality. It's always without equality. We're given N, we're given Z. Well, this is P, so I don't actually need this. This, given the 30, is not actually important. Why? Because I'm going to use this, right? I don't need this N. This is not a t-distribution. This is just useless information. So because I don't need this in, I'm just going to cross it out, and I'm going to go up to the spreadsheet, and the spreadsheet I'm going to put in is I'm going to put in a negative 1.645, okay? So I'm going to use my spreadsheet, and I have to make a decision. Do I decide if it's left or right tail? Well, the decision is based on the direction of the inequality. So the HA is what you are looking at, and it is pointing to the left. So it is a left tail test. What does that mean? Well, if I were to graph this, here's where my z-score of a negative 1.645 is, poorly drawn. And what I'm trying to do is find this area under curve, the probability of that. So I'm going to go out to my spreadsheet for chapter 9, and I'm going to use the one that is the same for both. So I'm going to put in my probability of the negative 1.645, and it's going to give me a p-value of 0.049985. Now, what is my decision? My p-value is less than my alpha, because remember, my alpha is given at 0.05. So what am I going to do? I'm going to reject the HO. So I'm going to reject HO, which is the status quo. There is sufficient evidence to cast doubt into the status quo, the HO. Now, if I go back to my chapter 7 calculator, so let's kind of make that connection. If I were to put and go back to the chapter 7 calculator, and you're like, why chapter 7? Well, because we're going to go back to a standard normal distribution, or just a normal distribution. And if you remember in chapter 6, there's one that says only use if chasing a z-score. So I went to my chapter 6 calculator, and I went into the part that says only use if chasing a z-score, and I put in the probability of this, because this is the probability. What got kicked out using that chapter 6 calculator is I got kicked out a z-score of a negative, which is really super close, right? The z-score associated to this alpha, this z-score, is a negative 1.646. Oh, why is that doing that? 64485. It is close to, but it's close to my z-score. but it's actually smaller than this z-score. So this z-score is to the left. This z-score for this alpha is to the right of this z-score. And so I'm falling into that reject region. So this z-score falls into my reject region. So I could have done it with looking at the z-scores. It will give me, as long as I understand and can read the z-scores, I can do it that as well. So that's a connection between z-scores, the probability, and making the decision to reject or not to reject. If we take a look at our next example, we are given the mean. This is our ho, this is our ha. The mean is equal, the ha is the opposite. This is not equal to, so we know right out of the gate that this is a two-tailed test. So again, if I draw my picture, I have a two-tailed test, so I'm going to be looking for these things on either side. My z-score is the 1.08, so 1.08. I'm going to go into the same spreadsheet for Chapter 9 that I did here, because it's not a t-distribution, so I'm going to go back to my Chapter 9 calculator, and they're both the same, so it doesn't matter if I'm finding the p-values for mu and sigma. If you know mu and sigma or the probability, it doesn't really matter. I'm going to put in the 1.08, and it's a two-tailed test, and the p-value that's given to me, so if I go ahead and I put that in there, that's the area I'm looking for, that's the probability. My two-tailed test is coming out with a 0.280142. Well, that p-value is much larger than the alpha. So on this one, I'm going to fail to reject. So fail to reject. The ho. Now, how would I look to see what is the appropriate z-score for a two-tailed test for the 0.05? Well, once again, I'm going to go back to Chapter 8. And this time, I'm not going to put in 0.05. I'm going to put in half of that because it's a two-tailed test. So what I'm going to put into my spreadsheet in Chapter 6 that says use only if chasing a z-score. So if I use only chasing a z-score, I'm going to put in 0.025. And the z-score that comes out is a negative, and that's okay because we know this is symmetry. The z-score that actually comes out, I'm going to put in the positive region, is up here. It is 1.95996. So this is a z-score for the alpha divided by 2. So we can also look to see where did we see alpha divided by 2. We've seen that in Chapter 6. We seen it in Chapter 8, I believe, is when we start doing z-scores of alphas divided by 2. So we could have used those calculators as well. When I used the Chapter 6 calculator, it actually gave me the negative, but because of symmetry being a two-tailed score, and the negative would have been negative 1.95996. And either way, it doesn't really matter because this z-score is falling into the fail to reject region. Unlike this z-score, which is falling into the reject region, it's to the left, it's a left-tailed test, it's to the left of this z-score. And so it actually falls, this p-value, this probability is smaller than this value. That's, again, that connection of why to reject and fail to reject. This probability is much larger than this probability of 0.05. Let's take a look at the next one. We have the mu of 70. It doesn't say anything about sigma, and it's not a proportion. So we know this is a t test. So we're going to go to our Chapter 9. We're going to grab the part that says finding the p-values given mu but not sigma. This has happened most of the time. I'm going to put in a z-score of 1.23. I do need to put in the number of pieces that I have, which is 16. That automatically fills in everything else. It is pointing to the right. See how it's pointing, that arrow is pointing to the right. So I know it's a right-tailed test. It's pointing to the right, so it is a right-tailed test. If I were to draw the shape, not drawn well, this is 1.23. That's where we are. I'm looking for this probability. And so I put in the z-score. It is a right-tailed test, and the probability, the p-value that comes out is 0.1 1.40071. Now I know, since it's a right-tailed test, that my p-value is much larger, and I can actually find the z-score for that, or t-score, I should say, the t-score for this. So my decision is fail to reject the status quo, and that's because my p-value is larger than my alpha. Now, once again, for this, if I am trying to find the z-score that is associated with this, I can't use a chapter 6 because that's a normal distribution, and we're not in the land of normal distributions when we have t-scores. So I would look for the one that says, hey, if I'm chasing the a value and I happen to know the z-score, or I happen to know the probability. And I can just do this by using, to find my z-score, I can just put in the t-dot invert. I can grab that 0.5 and I do the degrees of freedom. What it's going to give me is the negative because it always defaults to the negative. I want the positive because I am to the right. And what I end up with when I put in the alpha of 0.5 in the t-dot invert is I ended up with a negative 1.75305. So here's where my t-score is for that 0.05, and you can see that this number does not fall in the reject region. It falls over here that says we failed to reject. So that's that connection between the z-scores or t-scores and our p-value and our alpha. Let's go through an example. It is believed that the mean height of school students who play in a basketball on the team is 73 inches with a standard deviation of 1.8. A random sample of 40 players is chosen. The mean sample was 71 inches and the standard deviation was 1.5 years. Does the data support the claim that the mean height is less than 73 inches? What this is asking me is, I know what the mean and standard deviation is for my population. You have done this experiment. The experiment, from your experiment, you chose 40 players. This is the mean of the 40 players. This is a standard deviation of the 40 players. Does this sample give us enough doubt to reject the standard status quo, which is the mean of all basketball players and the standard deviation of all basketball players, or does it not cast doubt? So this is where we start doing the hypothesis testing. Some of you have got the data now to do this because you have, the way that you did your data is you have either proportions you could do or you have your means, right? So you could actually start testing your own data. So how do we do this? Well, the first thing we want to do is think about what is the ho and what is the ha. Well, the ho is the status quo. It is believed that the mean height of students who play basketball on the team is 73 inches. Okay, so my ho is, and I have mean, so I'm going to use sigma, or excuse me, mu. We believe that it is 73 inches. Now I got to make a decision. We have a sample mean of 71 inches, so we can either use equality, or I can just use equals, or I can use greater than or equal to. I'm going to use greater than or equal to because my sample mean is less than the population mean. So I'm going to use greater than or equal to 73, and I'm going to use my ha to be mu is less than 73. Now the reason again is because my sample, which is what I'm going to use to make a decision as whether or not I got enough information to accept or reject the ho, is you can see my sample was 71, which is less than that. So I'm going to use greater than or equal to. I could have used equality, but that would have gave me a two-tailed test. I'm just not feeling it. So what do I have? Well, since it is mu is less than 73, it's pointing to the left. So I know I have a left tail test. And now I'm going to use the appropriate spreadsheet. Well, I'm actually going to scroll down so you can see the spreadsheet that you are going to want to use. It's going to be something that looks like this for proportions. And This is for t-distributions. And scrolling all the way down, and this is when we have sigma known. Okay, so I would be using this one for this example. Again, these are in the notes. Make sure you go through the notes and your numbers are matching up with mine. Okay, let's come back up here. Coming back up here, and so we have a left tail test. I'm going to use the one that is the sigma is known. So I'm going to open my chapter 9. I'm given the sigma. Somehow it's magically known. The alpha that I am going to use, since it's not given to me, is I'm going to put in 0.05. My mu, which is given to me, my mu for the population is 73. So I'm going to put that in for mu. The X bar, that is the sample mean. So I'm going to put that 71 where it says X bar in my spreadsheet. The sigma is 1.8. So I'm going to put sigma in, it's 1.8. And this is the standard deviation for the sample. So that's my S. I'm going to put in 1.5 for my S in my spreadsheet. I have 40 players, that is my N. And then I'm going to make a decision about whether or not I'm going to reject, or fail to reject. So my z-scores in my spreadsheets are done for me. So if I'm asking for a left tail test, my z-score is going to be for the alpha. The z-score for alpha, so z sub alpha, is calculated in my spreadsheet, and it comes up with a negative 1.64485. Now my spreadsheet calculates the z-score for this z-test, because it's a z-test. It's not a t-score, it's a z-test, so it's a z-score. And I end up with a z-score, which the z-score for my information, for my X bar, let me actually do X bar. My z-score for my X bar happens to be negative 7.027784. That's really small. Graphically, what is happening? So again, here's my graph. Here's where the z alpha over 2 is. This is a negative 1.64485. And my negative 7 is like way over here. It's way over here. My negative 7 point. So I'm obviously so far into that reject region, it's not even funny, right? I'm so far into that reject region. My p-value, when I look at my spreadsheet, is approximately equal to 0, which is clearly less than alpha. What does this mean? We have sufficient evidence to conclude from the data that the mean height of high school students who play basketball on the team is actually less than the 73 inches at a 5% level. The data does support the claim. So the claim is that, is the mean height less than? And the answer is yes. We have enough information to support that claim. The claim almost always is the ha. I can pretty much say it always is the ha. The ho is the status quo. The mean of a graduate student at a university is at most 31 years with a standard deviation of 2 years, a random sample. Okay, once again, they're giving me the mu and they're telling me the standard deviation, so they're giving me sigma for the population. A random sample of 15 graduates is taken. The sample mean is 32. The sample standard deviation is 3 years. So this is my X bar. This is right here. This is my S, my standard deviation for the sample. And we now have a significance of 1%. So in other words, my alpha here, so I have this, my alpha is 0.01. Okay, so I have 0.01. So I have to decide what I have for the ho and the ha. The ho is this, the ha is this, and the symbol is mu, because I'm talking about means. Okay, so a random sample, is the data significant? State the null hypothesis. So our Status quo is the mean age of graduate students is at most 31. So this is less than or equal to 31. That means this by default is greater than 31. And since I'm pointing in this direction, this tells me I'm a right tail test. Right tail test. And again, I'm given sigma, so I'm going to go out and I'm going to put in my alpha. This time my alpha is 0.01. My mu is 31. My x bar is 32. My sigma is 2. My sample standard deviation is 3. My sample piece, how many pieces do I have? Oh, they're actually giving me the p-value. What? Well, we're still going to do it anyways. The sample standard deviation is 3, and oh, well, I actually, 15 graduate students, so I have my n. There we go. Okay, so the z-score for the alpha, so the z-score for the alpha of 0.01 is negative 2.32635. The z-score for my x bar is being calculated as 1.9364917. And you're thinking, well, z-score of a negative is going to be exactly that. Well, remember, when we are using our spreadsheets, this is assuming that we're always going to the left. So the z-score that we're actually going to be looking for is not the negative. We're going to put the absolute value on that, so it's actually 2.3. So 2.3. Now, I can tell you without doing any work, just comparing the z-score of the alpha and the z-score of the x bar, if I were to draw this picture, right? Here is my z-score for the alpha. Here's where my z-score of the x bar is, and it is in the fail to reject region. Also, it's telling me my p-value is this. My p-value is greater than my alpha, so I fail to reject. There's not sufficient evidence to conclude that our data does anything other than support the status quo. So this next example, does the shaded region represent a low or high p-value compared to the significance level of 0.01 or 1%? And if my p-value is approximately equal to 0, even though I'm way up here, this little small piece means that this is approximately 0. So this tells me my shaded region is actually a really low p-value, right? So if they're telling me it's approximately equal to 0, it tells me that my p-value is low. So critical values. Critical values define the region and the sampling distribution of a test statistic. In the hypothesis test, critical values determine whether results are statistically significant. These are the t-scores or the z-scores, and they will depend on the hypothesis test is right tail, left tail, or two tail. If it's a right tail, you either use 1 minus alpha or the absolute value of the left tail. If it's two tail, or if it's a left tail, you use alpha. If it's two tail, you take your alpha and divide it by 2, which is what we have been doing up until this point. You would ask me in class, hey, is this always going to be divided by 2? Well, no, it's not. It's just only at this point if it is a two tail. So the things that we need to remember when we are doing a hypothesis test is you may see the level of significance as 1%, or the 1% is a preconceived or preset alpha. So this is telling you what alpha should be. As a percent, we turn that into its decimal equivalent, and that's going to give us the area under the curve that we are looking at. The statistician setting up the hypothesis test selects the alpha prior to actually collecting the sample. And I know we didn't do that with our lab 1 and 2. That's okay. It's totally fine. If no significance level is given, we're going to use the alpha of 0.05. Since I didn't give you one, we didn't preconceive one, this is what we're going to use when we do the lab for our testing of our information that we got from our samples. When you calculate the p-value, you're going to probably want to draw the picture. You're going to put the p-value is the shaded region under the curve from the left or the right, or the split between the two tails. For this reason, we call this a hypothesis test left, right, or two-tailed. The alternative hypothesis tells you if the test is left or right. Notice how every time I talked about being left or right, I looked at the direction of the inequality on the ha, not the ho. The ha never has a symbol that has the equal symbol. Ha never has equality. Any part of it will ever be equality. Ho will have equality of some sort, whether it's equal to, less than or equal to, or greater than or equal to. The ho is the opposite. So when we think about what are we getting, the p-value is the area under the curve. And what we've talked about is if that area is larger than the alpha, so my p-value is larger, that means the area under the curve is larger. That means my z-score is falling in a region that says failed to reject. It's going to be in that region. That's what it means when we're talking about p-values and rejecting and failed to rejecting, the reject region, and the critical value. Check your critical value. You can calculate the test statistic is between the critical value and the mean, you should fail to reject. If the calculated test statistic is between the critical value and the tail, you should reject, right? So we talked about that with our pictures up above. So here's another one. We're going to, according to the article in Newsweek, the natural ratio of girls to boys is 100 to 105. In China, the birth rate is 100 to 114. Suppose you don't believe this. You don't believe the reported figures of the percent of the girls born in China. You conduct a study. In this study, you count the number of girls or boys born in 150 randomly chosen recent births. There are 60 girls and 90 boys born of the 150. And the question is this a one mean or is this proportion? Well, this one is clearly a proportion because it's giving me information in terms of the China births, the Newsweek births, and also the number of births of boys and girls, males and females, of 150. So it's a proportion because it's given me in terms of proportion. So now we're going to state the null and the alternative hypothesis. So I'm going to just choose girls as my P, and so my ho is the status quo, and we're looking at China. So my P, I'm going to make that P, it's not rho, P, it's not P hat, this is in terms of the population. We're going to say it is equal to the 0.467. That is the status quo. That means the ha is going to be P is not equal to the 0.467. And we can tell by our ha that it's a two-tailed test. What is the symbol I'm going to be using for my random variable that I'm testing? I am testing p hat or p prime or p bar. I am looking at the sample proportion. So that's why I have p hat, p prime, or p bar. So what is it? Well, this is p hat or p bar, whichever one you want to use, is the proportion of female babies of the sample of 150. So what is my p prime? Well, my p prime is just going to be whatever that proportion is. Well, the proportion is, if I look back up, it is 60 girls. So this is 60 divided by 150, which gives me 0.4. My n is 150. That's the number of data pieces. Q prime or Q hat if you want. That's going to be 1 minus my p prime, which is going to give me 0.6. Now my sigma bar, this comes from my sigma sub x. Sorry, my sigma sub x is going to be the square root of pq divided by n. That's the calculation. I'm going to use a spreadsheet, and it's 0.04. What is the distribution? Well, the distribution is p prime is approximately distributed as a normal distribution, where I use p, and I use the sigma, which is pq divided by n. Those are not primes, those are p and q. Okay, so now what? How do I find my p-value? Well, I'm going to use the spreadsheet that's here. Let me just scroll down to where the spreadsheet is. Here is the spreadsheet for proportions. You can see that I'm using P naught and Q naught as for the population. And then I have the P prime and the Q prime for the sample. So I put in my alpha, I put in my P naught, it calculates my Q naught, it gives me my sigma, I put in my N. It gives me my z-score if it's a two-tail test. It gives me my z-score for the alpha if it's a left tail test. I just take the absolute value of this if it's the right tail test. I then put in my P prime and my Q prime is calculated for me. Now notice I am actually, when I'm doing the norm dot invert and it's a just the alpha, so it's a left or right tail. This is for two tail. This is left or right tail. Notice I will grab the cell that has alpha. For this one, I will grab the cell that has alpha divided by 2, zeros and ones in the appropriate places. The z-score, since we know that this happens to be a, what did we decide is a two-tail test? Because we have equality and not equality. So my z-score for my alpha divided by 2 is negative 1.955. My z-score for my p prime is negative 1.64474. Okay. So if I just look at my z-scores for the alpha divided by 2 and this z-score, that I can tell you that I'm going to fail to reject. I can also make that decision based on whether or not I have the alpha, my p-value. Because it's a two-tail test, here is my p-value. It is 0.10 approximately. So let's go back up and put that information in there. So if I come back up here, it's not asking me for it, but I am going to give it to you. The z-score for the alpha divided by 2, because it is, we decided up here, it was a two-tailed test. The z-score for the alpha divided by 2 is the negative 1.959954. The z-score for the p prime is, we got it to be negative 1.64474. Now again, because of symmetry, if I were to draw this, not well, by the way, here is where my z alpha divided by 2 is, and since it's symmetric, two-tail, I have it also up here. My z-score for my p prime is here, so z of p prime is here, and being two-tailed, it would be up here too, z of p prime. This area between this z prime and this z prime is going to be larger than this area where my z alpha over 2 is. And it also says, hey, if that critical value, which is this z of p prime, that's my critical value, if it is between this z alpha over 2 score and the mean, and you can tell it would be, then we fail to reject. We can do it without actually getting to the p-values. The p-values actually just make it clearer for us. Now my p-value calculated into my spreadsheet is 0.10. My decision, since my p-value is larger than my alpha, is I'm going to fail to reject the status quo. So the reason is because my p-value is greater than 0. And then my conclusion, I would write something along these lines. At the 5% level of significance, there is not sufficient evidence to reject the conclusion in China that the birth ratio is 100 to 114, so 46.7% girls. So we don't have enough evidence to reject that status quo. So again, if you are going to want to build calculators, you will want to build calculators. Notice how when I build my calculators, I like to label the crap out of everything. And this helps me make decisions later about what I grab, what I'm going to put in there. This is something close to like chapter 8. We're actually now in chapter 9. But it's going to look like something like chapter 8. I will have more information. So I have the alpha I'm going to put in. If it's a two-tail, it automatically divides it by 2. I put in my P naught, which is my population percent. Here's my Q naught. So it's calculated as equals 1 minus this cell. My sigma is I'm going to type in SQRT. I'm going to do these two multiplied together divided by my n, so I also need to put my n in there as well. These are calculating my z-score for a two-tail test, so the alpha divided by 2 is a two-tail test, and the z-score of alpha is a left or right tail. If it comes up with a negative, but you are right tail, you just take the absolute value of that. This was my proportion as a decimal, so 0.4, and my Q is calculated for me. So here is the z-score that I talked about, and you notice that this z-score is actually between this z-score and 0. And then I have the left tail, right tail, and I was looking at the two tail, which is where I got that 0.1. Again, here's all my call numbers. And of course, don't forget the absolute value when you're doing the 1 minus norm.dist. So the two tail will need the absolute value of that z-score. The other ones will not. And then what I do is this is being grabbed from up above. So I'm grabbing this cell, we'll grab this cell from up above. I'm just going to grab the appropriate one and I'm going to put it here. And this helps me to decide if the p-value is greater, obviously this is greater, then I'm going to fail to reject. If this value is smaller, I'm going to reject. Now you actually could put this in a spreadsheet, so it would automatically do it as long as you put that number in there, whatever number you choose to do there. So you could actually do it automatically. Off the top of my head, I don't know how to do that. I'm sure I could find it and let you know. Okay, let's do the next one. So it's, again, we're going to go through the entire thing. A random survey of 75 death row inmates reveals that the mean length of time on death row is 17.4 years with a standard deviation. Okay, this is giving me my, the mean length. Okay, this is giving me my sample amount of death row and my sample deviation on death row of that 75 death row inmates. Conduct a hypothesis to determine if the population mean time on death row could likely be at least. Well, this information is my mu. So what it's not giving me is my sigma. So since it's not giving me my sigma, I already know without doing anything more that I'm in a t distribution. So what is this? This is a one means test, okay? So what I'm testing is the status quo. So my HO is the status quo, and I'm trying to determine whether or not the information I got is going to show that the population mean time on death row could be likely at least. So I have mu is greater than or equal to the 18.8. That means my HA is the mu is less than 18.8. So the fact that this is pointing to the left, that we know that this is a left-tailed test. What is my symbols? Well, my symbols are going to be X bar. So I'm going to use X bar. I'm going to be using S's, and I'm going to be using a t distribution. The random variable is X bar. Well, what is X bar? X bar is the mean time in years of mean time in years of inmates on death row. For the sample. What would X be? Well, you're going to be really surprised. If I had to define X instead of X bar, then the only thing that's going to change is I wouldn't have an X bar, I'd just have X, and I'd still say the mean time in years of the inmates on death row for, instead of the sample, I would say the population. I know, surprising, right? So going through this, I have my X bar is going to be 17.4. My sigma from up above is 16.3, and my sample size is 73. This is a t distribution because I don't have the standard deviation for the population. So I know it is a t distribution, so I have capital T, and then my degrees of freedom, because it's going to be, and it's not 73, it's 75. I don't know why I don't know if you remember if I said 75. It's 75. And so my subscript is the degrees of freedom. My degrees of freedom is going to be 1 minus, so that's 74. Okay, again, they're telling me my alpha is 0.5. So the spreadsheet I'm going to need is something like this. And we'll go over that spreadsheet in just a minute. The p-value. Okay, well, I'm going to use my t distribution. I'm going to use my alpha 0.05. I have my mu is 18.8. I have my my X bar is 17.4. I'm going to put in my S of 6.3, a standard deviation of 75. This is a left tail test. So what is the z-score for the left tail test? If I find the z-score of just alpha, it is not alpha over 2, because the only time I have alpha over 2 is the times in which I have a two-tailed test. The z-score for the alpha is the negative 1.665707. This calculates, my spreadsheet calculates my z-score. My z-score for this, so my z-score for this mean of 17.4, or I could just put x bar, is going to be, so let me just do x bar, is going to be negative 1.9245, a bunch of zeros after that. So just looking at my z-scores, right? So if I draw my graph, not well, obviously. Here is my z alpha. This is where my z of x bar is, and I can tell just by the z-scores that I'm going to reject the hoe. The p-value, however, that they're asking me to find is the p-value for a left tail test is 0.0291. My decision is to reject the hoe, reject that status quo. So the reason is my p-value is less than my alpha, and so in my complete sentences, I would say something along the lines that at a 5% significance, level of significance, there is sufficient evidence to reject the conclusion that the population mean time on death row is more than 18.8 years. And this is what you would have. Again, I like to label everything. All this stuff can be found in the notes. Please put these numbers in and make sure your calculators are pulling the same numbers. The decision again is I pull this, whatever one I'm using, which is this case, I pull it down here, and you can see this number is, that should be a 0. Didn't obviously pull that in right. That should be 0.0291, and that number is smaller, so we reject. Let's take a look at this next example. Life magazine reported that 25-year-old mothers of 3, this is in 1955, so it is not uncommon in 1955 to be 25 years old and have 3 children. Now, not so much, but back then in the day it was. So in 1955, reported that 25-year-old mother of 3 worked on average an 80-hour week with a standard deviation of 5 hours. So this has given me the standard deviation of the population, standard deviation, and it's given me the mean. Recently, many groups have studied whether or not the women's movement has in fact resulted in an increase in the average work week for a woman, combining the employment and at-home work. Suppose a study was done to determine if the mean work has increased. 92 women were surveyed with the following results. The sample mean was 83. The sample standard deviation was 10. Does it appear to be true that the mean work has increased for women? I don't know if you've been paying attention, but there is a lot out there about this. And in general, they're saying that if you are married, whether you have kids or not, that it is likely that the wife, or one typically is the wife, will, and we're talking about heterosexual couples, it's not true on others, but if you read the literature out there right now, it says that if you are in a heterosexual couple, it is likely that you as the wife will spend more hours working in the home and everywhere else than your counterpart as the male would do. So men, step up to the plate. Women, make them step up to the plate. Or just say, you know what, I'm not doing it either. Just saying. Okay, I'm off my soapbox. What is this? This is a means test. Means. So let's talk about the null and the alternative hypothesis. So the belief is that it is still 80 hours a week. That's the belief. So my my ho is mu is equal to 80. My ha is saying, yeah, that's unlikely. So it's not equal to 80. This is a two-tailed test because I have the not equality. The symbol I'm going to use is x bar because we are talking about means. My x bar is going to be the average hours worked for a woman per week. of the women surveyed. So this is the average hours worked for the wife from the sample. So let's put everything in here. We have a mu, or excuse me, of the X bar. This is the sample, that's 83. My mu is the mean, and that was 80. My sigma comes from the population, which was given us by. My standard deviation, S, for the sample was 10, and my N was, what did I have up above? I want to make sure I have that. 92, right? I want to make sure I have 5, and the mean, I want to make sure standard deviation, recently, work, in fact, that resulted. Let me make sure I'm up here of 92, 83, and what was I had for the standard deviation S? 10. Okay. So that was 10, and I had 92 women. So what is my distribution? It is the X bar is approximately a normal distribution where I have the 80, and then I have 5 divided by the 92. What is my p-value? Okay, so I know this is a z-test, but it is a z-test. Well, sigma is known, unlikely. I am going to put in my alpha of 0.05, and I have my mu, which was 80. I'm going to put in my X bar, which was 83. I'm going to put in my sigma of 5, my standard deviation of 10, and I have 92 pieces of data. Now, because of the fact that this we decided was a two-tail test, my z-score, my z for alpha divided by 2 is giving me a negative 1.95996. I think that's right. 996. Yeah, I think so. What's calculated for me for my z bar, so my z-score for my z bar, it's calculating a holy crap of 1.574899. Now, because it's a two-tail test, I'm going to actually take the positive of that. And so graphically, what does this look like? Graphically, it looks like this. Here's where mu is. And my z alpha is like here. Here's my z alpha divided by 2. And also it'd be over here for the negative. My z sub r is way out here. You know, here's my z sub r. So you can just tell by the z-scores, I am in the land of reject. Reject that status quo. Well, what is my p-value? Well, according to this, my p-value is approximately equal to 0, and that would make sense how far I'm out. So what am I going to do? I'm going to reject that belief that women work 80 hours. That's actually not true. So reject. Why? Because my p-value is much less than my alpha. So I'm going to reject the whole. And I would say something along the lines, and you're going to notice that every time I say this, it's pretty much the same thing over and over again. And I'm going to say, on the 5% level of significance, there is sufficient evidence to reject the conclusion that women work on average 80 hours per week. Now, I want to do a shout out to my husband. He is phenomenal. When we were first married, not so much, but he has been stepping up to the plate, and he will do the dishes, and he will vacuum, and he will be a part of the partnership without being asked or without saying you need to help, because he's not helping. It is his house too. It is a partnership. We both do it. So I wanted to give a shout out to him. He is awesome. He has stepped up to it, probably because I stopped doing it and I said, I'm not doing it. You do whatever you all need to do. Anyways, that's just me. Here is the spreadsheet for when you have a z-test where the mean for means and the sigma is known. Once again, you will make sure that your numbers are matching mine. You can see there's my alpha, there's my z-score for my x bar. That's the left tail test. This is my right tail test, approximately equal to 0. This is a two tail test, still equal to 0. So even if I said, okay, the not equal to, or even if I did a right tail test, it doesn't matter. There's enough evidence to conclude that we are going to reject that belief, reject the status quo. Here's the alpha, here's the p-value, and we are going to reject. And I know this is a long video. There is a lot going on, and that's because I wanted to go through multiple steps on how to do that. Do make sure that you download those notes and either fill those in as you watch this video, or at least open those notes so you know what to put in your spreadsheets. And that's it. Have a great day.